Hi friends, a very good evening and thank you for joining in. So let me just check if everything is working as expected so that I'm sure that there are no technical glitches. Just give me a minute. Also, could you please confirm in the chat window if you're able to see my screen and listen to my audio, right? So if you can do that, that will help me so that there are no technical glitches whatsoever. Hey folks, could you please confirm in the chat window about whether you're able to see my screen and hear to my audio? I don't see any hiccups from my side. Okay, so the audio is clear and audible and you can see my screen decent size. I also have the chat window just to see the answers. Also our team, some of our mentors also will join. They'll try to answer some of your questions which I may not be able to answer because I also have to manage the questions that we have to solve, right? Sounds good. We'll start in a minute or so. We'll start at 7 sharp, right? So let's just wait for a minute while others join in and we'll start at 7 sharp. Okay, yeah, the mentors have also joined. Thanks folks. So let me know. Again, they'll also be answering some questions which I may not be answer because I'll not be able to take every question in live, especially in a public live. Okay. Sounds good. Where are we? Okay, it's 7 p.m. So let's get started with the session itself. So today, okay, let me take my annotator. Okay, so the annotator is ready. Cool. So let's get into the session today. This is the second session on problem solving in theory of computation. We've already done one other session, I think just last week. I think same Friday last week. We solved about 13 problems. It was a very good session. Today the syllabus is the rest of the topics that we have in theory of computation. Mostly context-free grammars, push-down automata, the pumping lemma for context-free grammars, context-free languages, Turing machines, undecidability, etc. Typically, you can expect about 4 to 5 marks in GATE from this, right? So again, we have done a session where we explained about what topics are important, what weightage you can expect from each of the topics in TOC. We have done analysis for about the last 7 or 8 question papers. It's there on our YouTube channel, publicly available. Please go check it if you're interested in what is the weightage for each of the topics. Now, typically, you can expect around 4 to 5 marks from these concepts. The rest of the concepts, which is PDA, which is finite automata, deterministic finite automata, non-deterministic finite automata, regular expressions, regular languages, that's about another 4 to 5 marks, right? So again, this is very easy to score. If you're careful, even if you're slightly careful, you can easily score 90% plus marks in TOC alone. And in this session, I will specifically discuss some useful tricks that are helpful to handle tricky questions. Again, most of TOC is easy. If you know a couple of tricks, I'll cover them. So after TOC is over, logically the next subject that we will cover will be compiler design, right? Number 1. Number 2, students have been asking us about the test series. We are just finalizing everything. We will launch it on Monday. Just giving you a heads up here. If possible, we'll launch it on Sunday, but otherwise, worst case, we'll launch it by Monday end of day. And as per students' requests, we are updating all of the DLD videos. There was another instructor who taught digital logic design last year. So, and we were contractually obligated not to update the videos for a while. So now we can start updating them. We have already updated the first chapter. We'll be updating chapter by chapter. And in another 10 to 15 days, all the chapters, again, we already have done some of the videos. We are just post-processing them. And because the whole team is not at one place, all of our computers are not at one place, it's taking slightly longer for us to complete the post-processing before we upload. But we should be able to finish everything in about another 10 to maximum 15 days. So those of you who are waiting for me to do the DLD videos, please wait for another 10 to 15 days. It will all be ready. Then you can watch DLD altogether. But those who have already studied learning from the previous instructor, it's going to be perfectly okay. He's a phenomenal instructor. He teaches concepts fairly well. But on students' requests, we are just redoing them. So if you have done it from the previous instructor, don't worry. The series, the sequence of topics and the breadth of topics, the depth of topics will be very similar. It's just that you have a different instructor teaching, right? So sounds good. So with those updates, let's get into the TOC2. Let's start with each problem. Again, we have 10 problems today. Some problems could be lengthy, so we might take anywhere from 60 to 90 minutes. I'm not starting a timer because timer discourages, because of timer some students make mistakes. So I'll just wait for a few students to put in their answers in the chat window right here. Once I see decent number of students putting in the answer, I'll go into the solution. Okay, because at this point of time, accuracy is more important than speed at this point of time. Okay, so let's go. Here is the first question. Okay, I see a few people putting in answers. Okay. Again, just be a little careful. It's a simple problem if you think through it. Try to eliminate options wherever you can, because in the gate exam, speed helps sometimes if you're careful with not doing silly mistakes. Yeah, this is straightforward problem. Let's wait for a few more seconds because some students have put in the answers, but let's give people time. Okay, I see A, B, some people also said C, some people said D. Okay. But I see mostly B's, which is correct. So let's get into the solution one by one, right? So here it says a power k, where k is a perfect square. Again, this is an example. Again, you can apply whenever you want to prove something is a context-free language or not. You can always use the pumping lemma for context-free languages, right? But that could sometimes take more time, right? So this is one strategy. This is extremely useful if you want to prove that something is not a context-free language. The second approach that you can do is you can construct a push-down automata. What is a push-down automata? It's nothing but a finite automata plus a single stack. That's what it is, right? If you think about it logically, or try to write a context-free grammar for it. These are three strategies that will work for you. Again, in practice, applying the pumping lemma for context-free languages can be slightly tricky because it can take a lot of time. In GATE, each of these could be, again, in many exams at universities, this is a full-fledged 5 marks question or even a 7 marks question, right? So you have to determine this quickly, and the solutions, the trick here is wherever you already know, that's cool, but if you want to apply pumping lemma, it will take more time. The better strategy is to think about it in terms of using finite automata plus stack. Can you use a finite automata and stack and figure it out? Or can you write the context-free grammar? Right? Simple logic. So if you look at this, this is something that we prove in our course videos. Let me actually show you that. So we actually prove that L equals to a power m square. This is pumping lemma for CFLs. I actually show step by step using the proper proof methodology of pumping lemma and show you that this is not a context-free language. I actually prove that as an example problem when I explain about pumping lemmas, right? So those of you who are course registered, you can easily see this, number one. Number two, those of you who are not course registered can also figure this out because there is a very nice property of context-free languages. If, again, remember that the alphabet here consists of a single symbol. The alphabet here consists of a single symbol. Again, there is a very nice property of context-free languages when the alphabet is a singleton set. When the alphabet is a singleton set, there is an extension to pumping lemma even for context-free languages, which says that the length of words that you have should follow arithmetic progression. This is a special case of pumping lemma. This is a special case of pumping lemma for context-free languages that we explained in our course videos. Similarly, there is a similar pumping lemma, similar special case of pumping lemma for regular languages that I've explained in the previous video also. So what it says here is, if your alphabet is a singleton set with only one symbol, then the lengths of characters should form arithmetic progression. So if you have a power k, what do you have? You have a power 0, a power 1, you have a power 4, you have a power 9, a power 16. If you notice 0, 1, 4, 9, 16, they don't follow an arithmetic progression. Because they don't follow this, this is not a context-free language. So there are multiple ways of solving this. One is you can use the pumping lemma and prove it theoretically as we have shown in the course videos. The second is you can use this special case. You can use this special case of pumping lemma for context-free languages and figure it out, right? Again, I'm trying to show you multiple solutions so that given new problems, you can solve them also well. Again, I can answer this. Again, if I were to answer this question, it's very simple to answer it in like under 1 minute. But I just wanted to show you multiple ways of doing it so that even if new questions come, you're better equipped. Now look at this situation here. So you want, see, look at this. You're doing two comparisons here. Again, for this type of question, I would think about it from the perspective of having a finite automata plus stack, right? So if you have a finite automata with a single stack, remember, if you have two stacks, then you can prove that, again, there is a very nice proof that if you have a finite automata plus two stacks, you can prove that it's equivalent to Turing machine. I also mentioned that in the course videos, right? But imagine that we don't have that, okay? You have a single stack. So you can compare, you can figure out this fact, right? By pushing and popping. With one stack, you can figure this out. But you have to do two comparisons here simultaneously. You have to ensure that I is less than j. You also have to ensure that j is less than k. And that is tricky. To solve this problem, you actually need two stacks, which means, again, a finite automata with, or a PDA, instead of having one stack, if it has two stacks, that's equivalent to a Turing machine, right? So this surely is not a context-free language, but because if you think about it, you can't solve this problem with a finite automata plus a single stack. So surely this is not a context-free language. This is not a context-free language. So the moment we know one is not a context-free language, this option can be eliminated. Similarly, this option can be eliminated. The moment you know 2 is not a solution, you can eliminate this option also. So you're left with option B. See, instead of solving for four options, by just solving for two options and eliminating, you got option B, which is the right option. But let's also think about this. Just for completeness sake, I wanted to explain, in case, in case the question requires you to solve a problem like this. Again, this is very simple. Again, in such a case, again, remember in this case, we thought about it from the perspective of a PDA. Now we'll think about it from the perspective of context-free grammar. Okay, look at this. So what do we want here? We want i's and j's. We want, we have number of a's and number of b's. We want number of b's to be less than twice the number of a's. But we want the number of b's to be more than number of a's. That's the simple logic here. So let's try to start writing a context-free grammar. It's actually very simple. Let's assume I have this. So a, s, b or epsilon. Because this can be equal to 0, epsilon also belongs to this language. So s can generate epsilon, or 1 second, I don't need this capital B here, do I? Oh, I will need it because the number of b's, okay, so I need this. Now what can I do here? Now if I start thinking about it, the number of b's has to be more than number of a's, or have to be greater than equal to. It could also be equal to. So what if I do this? Look at this. If you think about it, again, we have shown a lot of examples on how to construct context-free grammars through logically thinking through it. So if you think about this context-free language, I hope I got it right, right? So this can generate a power 1, b power 1, yes. It can generate a followed by, yeah, it can generate them, yes. So it will always start with a's followed by b's. The number of b's is at least the number of a's, but at most double the number of a's because we have this. Yes, we can solve it like this. Now, again, since this is a context-free grammar, right? Because what is the property of a context-free grammar? The variables on there has to be one variable on the LHS. On the RHS, it can be any string of variables and terminals. This is what you need in a context-free grammar, right? So this surely is, because we have a context-free grammar, this is a context-free language. Similarly, look at this. In this case, I can think about it from the perspective of PDS. right? Again, I'm taking more time to explain so that you can think about it from first principles, and given any option, you can solve them. So here, this is very simple, right? If you get A's, push them, right? If you start seeing B's and C's, pop them. The number of A's should be equal to number of B's plus number of C's. That's your goal. And you just make sure that there is at least one A, right? Because, you have to ensure that there is at least one A, one B and one C, because I and J are strictly greater than 0. And that's easy. That you can put it in the finite automata part without the stack. So very simple. So you can see that this is also context-free language. Again, I'm explaining it using multiple approaches, but in an examination scenario, you can just see, okay, this is K. You can just apply that special case of pumping lemma and decide that this is not context-free. You know that you can't construct a PDA or a finite automata plus stack with this. So you can get rid of this. So this option goes, this option goes, this option goes. This remains the answer, right? So this is again, I'm trying to go deeper into the solution so that students absorb the concept and learn the tricks to solve even tricky questions, right? So let's go to the second question. Yes, please. Once you learn a couple of tricks in context-free grammars, how to think about it, it's actually very simple. That's why I said it's very scoring. This is a good question. It is simple. Okay, I see a lot of people, lot of students putting in their answer. So let's go into the solution. It's actually a fairly simple problem. Look at it. S can generate, if you notice, S can generate A S1, B S3, C. Now look at what S1 can generate. See, look at this. S1 can generate A S1, B, right? Or epsilon, right? So if you notice this, S1 generates S1 itself. So if you think about it, what this generates, if you look at this expression here, right? So what it can generate here is, it can generate something like A power n, B power n, right? If you look at this, right? So now let's come, so it can generate A power n, B power n. This is one way. So because you have A and B here, so effectively what's happening here is the number of A's and number of B's will become the same. So you have number of A's, look at your solutions also. You have A power I, B power j, C power k, and you have a bunch of options. So in A power A, B power j, so this part of this expression basically says that you have A power I and B power j, and it says I equals to j. That's what it's saying effectively, right? Now let's look at S3 part. If you look at S3 part, S3 says S3C, right? Look at this, it says S3C, right? Sorry, you have S1, S3, right? So it says S3C, okay. So S3 generates S3 and C, right? So that's what it generates. Now S3 can keep generating C's, but there is no control on the number of C's that it generates, because S3 can keep generating some C's. So one option you have here is that I equals to J. So that part we are clear. Okay, I equals to J, that part is, that's again, we have only looked at this expression. We haven't yet looked at this part of the expression. So if you start looking at this part of the, so from the first part of the expression, what we learned here is you'll get the same number of I's and J's, but number of C's we don't control. Okay, so that's one part. So let's just say I equals to J is one possibility. The second possibility, so let me just write it, I equals to J is one possibility. The second possibility, if I use this expression here, look at this, S generates A, S4, B, S2, C. Now what is S4 generating? S4 generates a bunch of A's. It can generate some A power K. Some A, no, let me not call it K, let me just call it A power M. Because it can keep, or it can even generate, so as long as M is greater than or equal to 0. Because it can also generate epsilons. But look at S2, what is S2 generating? If you notice S2 here, S2 will generate the same number of B's and C's. Right, so this will generate something wherein you have B power N, C power N. Which means, because there is one B, there is one C here, this expression effectively results in having the same number of B's and C's. So this basically says J equals to K. So you can either have the first part wherein you have I equals to J, or you can have the second part where J equals to K. This is OR, because from this expression, because S can generate this or S can generate this. Right? S need not generate both. It can generate this or this. So what you will have here is A power I, B power J, C power K, where I equals to J or J equals to K. Again, OR is very, very important. It's not AND, because this is the case of AND. It's not AND, because S can generate either this or this. Right? So that's how, again, you can just draw such simple diagrams and you can easily get the answer in like a minute. Okay? It looks, again, some of these questions might look tricky or lengthy, but they're actually simple. Okay, so let's go to the third question now. This is also a simple question. Okay, for the third question, let's see the options. Again, take your time, it's okay, don't make silly mistakes. I'm already seeing a few silly mistakes. Just think through it carefully. Guys, I see people doing silly mistakes in the chat window. So please double check your answers. It's slightly tricky. The options are slightly tricky, but if you think through it, you'll get it. Try to construct counterexamples. That could help you sometimes. I see all the options A, B, C, and intentionally we've given slightly tricky options for this question because the question itself is easy. So let's take a few more seconds for people who may have made a silly mistake to correct it for themselves, and then I'll go into the solution. I see the silly mistake still. That's okay. Let me explain the solution, right? So let's look at this. So, okay, so S generates A square, right? A is nothing but A square, right? So this S itself can keep generating this. So what you'll have here is, if you notice this whole structure, because S can keep generating this, what you'll end up with is, you'll end up with something like this. You'll end up with A power n at the beginning, A power 2n at the end. That you're guaranteed. But remember that S can also generate B. And what can B be? B is basically a bunch of B's, right? B can generate B, this can keep generating B. At some point it will replace it with epsilon. So in between the B, it could be any number, right? So A power n, B power m, A power 2n is the logical thing. Some of you have answered B, but B is incorrect, right? Because look at this. This can generate something like this. B can be replaced, AB, AA. Look at this. This can generate AB, AA. It can generate AB, AA. But AB, AA will never be in this language, because this language only consists of strings with A's or strings with B's. This language will never consist of strings which contain both A's and B's. So B cannot be an answer. That's a silly mistake that many people are making. Intentionally we gave that. We gave this option intentionally to catch you in that silly mistake. And gate questions, if you see the last 5 years, they're all tricky. I mean, so at least the so-called hard questions are tricky. They're not hard. Okay, so that's one part. So B, all the people who said B, I hope you got it clear. Now the second thing is, if you look at option A and option C, look at this: A power n, B power m, A power 2n, A power n, B power m, A power 2n. So this is not the option, because the number of B's we don't have a control. So D also can be eliminated. The only difference between these two is the n and m is greater than equal to 0. It is greater than equal to 1. So in such a case, what you should see is, can S generate epsilon? Look at it. S generates B generates epsilon. So S can generate epsilon, which means your n and m can be 0. Right? So this can't be an option. Only C can be a right option here. Again, you have to think carefully about the counter examples in these cases. Intentionally we given it tricky. Okay? Sounds good. So A is not an answer, because A does not accept epsilon. Right? The language L in option A does not have epsilon. Right? But S can generate epsilon. This grammar can generate epsilon. So A is not an answer. This can generate epsilon. So C is the only left out option. So C is the right answer. Right? Again, intentionally we gave it tricky. You see a lot of questions in GATE in the last few years. They're simple. They look deceptively simple, but the options are tricky, to trick you into getting wrong answers. Okay? So just be careful there. Okay, so let's go to fourth question now. This is also slightly tricky if you're not careful. This is also easy question, but you could fall into the trap if you're not careful. Think carefully. The and, or, think carefully. Okay, I see a spectrum of answers, so please be careful. I see both A, B, sometimes even D. So just think through that, please, carefully. Okay, I see a few incorrect answers, so please think about your solution. Just think of building counterexamples. Okay, I see good amount of questions and some people also corrected. So let's look into the solution. Okay, so S generates S1, S2. Look at it. S generates S1, S2. Now what is happening with S1? Look at it. It's a concatenation. It's not OR. It's a concatenation of both. Now what's happening with S1 now? Let's look at it. S1 generates, it can generate just 0. Look at it, in each of these cases, if you just look at this expression, if you just look at this expression, what does it say? It says that I'll generate some zeros followed by ones. That's one possibility. But the number of zeros is going to be more than number of ones. Because I can add, look at this, in this case, it is 0 power 1, 1 power 0. In this case also, I'm adding a 0, but I'm not adding a 1. In this case, I'm adding the same number of zeros and ones. Right? But remember, even though I'm adding same number of zeros and ones here, finally S1 will be replaced by 0. There is no epsilon here. So the number of zeros, so what you'll be left with is, you'll be left with an expression like this, 0 power n, 1 power m, where n is strictly greater than m. Now you might say, why is n strictly greater than m? That's very important because, look at this, what can S1 generate? It will generate 0, S1, 1, right? S1 itself, look at this, S1 itself has to be replaced with a single 0, worst case. So you will have an expression like this, where the number of zeros is strictly more than the number of ones. It can never be equal, that's important. So what you'll have here is n greater than m. The important aspect that many people make a mistake here is, this is what S1 is generating. Look at what S2 is generating. S2 also looks like the same thing, bro. Very similar thing. But except that instead of 0 S1, you have S2, S3. So here if you notice, here look at this, you will get 0, 2 power p, 3 power q, where q is greater than p. Because it is generating more 3's than 2's, strictly. Right? But the final expression you have has to satisfy this condition and this condition, because it's a concatenation. So the ORs you can easily, because it's not this or this, it's not that, it is this and this. So by just looking at it, you should be able to eliminate C and D easily. Now if you look at A and B, they're very similar except for the equal to part. Again, Q greater than P is nothing but P less than Q, right? So the equal to part is the tricky part where a lot of people make mistakes. So if you think logically, A is the right option, B cannot be the option, because you'll always have this expression. You can never generate same number of zeros and ones, similarly same number of 2's and 3's. You can again try that. But logically, if you see these expressions, you should be able to figure that out. Again, here also the options are given with some trick, right? Again, this is one way of solving. This is my preferred way of solving. There are some students who also solve it slightly differently, where they try to come up with counter examples for everything. That's another way of thinking. Right? The problem with counter examples is intuitively harder to come up with. Right? My suggestion is, think about what the grammar is generating intuitively. The counter example way is certainly one way, but it's also very, very prone to mistakes. Sometimes it's useful, but sometimes you will be prone to mistakes. Okay, so cool. Let's go to the fifth question. I love this. I love these topics. These are so easy to make mistakes in, but also fun logically. Oh, this is a very good question. I like this question. Again, please take your time to think about this question, because you can again Most of TOC, we see people making silly mistakes in the hurry of time. That's why I stopped the timer now, because I want you guys to think clearly when you solve. At this point of time, in early June, accuracy is more important, precision is more important than speed. Speed will automatically be built up. Okay, I see a lot of people answering this question. There is a small typo in the previous question. So let me, there is a small mistake. I mean, probably when we set the question, we made a small mistake here. So what is the minimum string that it can generate? The minimum string S can generate is 0, 3. It can't generate epsilon. So in the previous problem, what was the answer? A was the answer, right? So here we should say that n is strictly greater than 0. P is also, sorry, not Q is strictly greater than 0. And M and P could be greater than equal to 0. So here we said all of them should be greater than equal to 0. That's a typo. This should have been this. So there is a small correction in the previous question. It's a good point. I think I missed it when I was solving it also. I overlooked it. Probably, yeah. So there is a small typo here because the minimum string, this can't generate epsilon. Because if all of them can be equal to 0, this will become epsilon, right? It can never generate epsilon. 1 second. The other way of looking at it is, no. I think, let's think about it. This is still all right, right? Okay, so no. So this option is still all right. Okay, let me explain why. Because you have a logical AND here. Look at this. So what does this say? This says n is greater than, okay, so this is good. So if you look at this, right, n m p q greater than equal to 0. Okay, the question is okay actually. I got confused by looking at some people's suggestions because you have this strictly greater than, you have this strictly less than. So if you take m equals to 0, because the minimum value of m is 0. So m equals to 0, the minimum value of p is 0. Because you have the logical and, n can never be 0. The minimum value of n is 1 because n is greater than m and n is greater than equal to 0. Which means the minimum value of n is 1. Similarly, minimum value of q is also 1. So it can generate 0, 3. So this is perfectly all right because it's a logical and. I got confused when students pointed this out, but this option is correct. There is no problem with it. Sorry for confusing you. This option is perfectly all right. No issues with that. Okay. So I thought there is a typo. There is no typo here. Okay. So epsilon will not be part of this language also because of this condition and this condition being strictly greater than, right? Sounds good. So let's get into the fifth question. Again, if there is any typo, please do reach out to us. Our email address is gatecsc@appliedcourse.com. Again, we are human. Even the professors at IITs make mistake when they give questions. In case there is any mistake, do let us know. We will fix them. Okay. Again, to be honest with you, we will not be able to reply to all students because our first priority is students who have registered for the course. And that's always our first priority because we have promised them a certain time under which we'll respond. So it's not possible for us to respond to everyone, but we'll try our best. That's all we can. If there is an error, if you find a mistake on our system, we will surely help you with it. But for general questions, we may not be able to answer everyone because our top priority should always be students who are already registered for our course. Okay, so let's go to this question now, right? Okay, so let's go to this. Okay, again, this is a diagrammatic representation of your pushdown automata. So let's get into this. Remember that this is a non-determinism here. There is a non-determinism because it also says NPDA. Because from 0 on the same input, same stack symbol, you're doing different transitions. So if you think about it logically, this whole thing is one path. This is another path. Now let's look at what this path is doing. Again, it's very simple to think about it that way. So in this path, when we are getting A's, we are just pushing them into the stack, and that's clear from the state, right? When we get A's, we are simply pushing them into the stack. When we get B's, look at this, when we get B's with A on the stack, we pop it out. But the number of B's, there is no control here, right? Look at this. For every time there is an A on the stack, again, each of these states have been very nicely designed. If I keep getting A, so let's write it in this form, right? So a power I, as I'm keep getting A's, I'm pushing it into the stack. Once I start getting B's, I'll go into this state now, right? And as long as I have my A's, right? Look at this. I have B power J, right? Whenever I have A on the stack, because I've pushed all of them into the stack, I've pushed all the A's onto the stack. As long as the as long as the stack top symbol is A, I keep popping it. That's what I'm doing here. But at some point, I'll reach the bottom of the stack. Even after I reach bottom of the stack, I can keep getting B's here because of this loop, right? So which means my J will be strictly greater than I. Look at this, A power I, B power J, because I can keep pushing. So look at this. If I reach the bottom of the stack and if I keep getting B's, I'll still be here. Now, once I start getting C's, I'll move here. I'm at the stack. I'm at the bottom of my stack. There is nothing in my stack. Then I come here. If I get C's, I'll be here, right? So I have my C's here, C power K. Okay. So what is this doing? This is saying that this basically says I need my number of B's to be greater than number of A's. That's what it says strictly. Okay. And it also says, if you notice this, with epsilon, I can't reach here. With epsilon, I can't reach here, and all of these are greater than 0. So that problem is solved. So what this is simply telling us is that I is less than J. That's what it's telling us. If you follow this path, look at this. If you follow this path, all that it is saying here is I is less than J. Similarly, if you follow this path, let's see what happens if you follow this path. In this path, what's happening now? If you get A's, look at this. If you get A's, you're not doing anything. You're not even pushing it to the stack. You're just letting A's come. So you have A power I. You're not even pushing it to the stack if you notice here. The moment you get B's, you start pushing them into the stack. Look at this. The moment you get B's, you're pushing them into the stack. Now, once you get C's, you're popping B's from the stack. So you have C power K. So B's, you've pushed them into the stack. When you get C, for every C, you're popping B's now. Look at this. You're popping B's, right? You're popping your B's now. But the number of C's have to be greater than, one second. The number of B's, okay, let's look at this carefully, this part. So if you get B, you're popping it, right? So you pop, so here also you keep popping. So now at the end of the string, what happens here? You have epsilon, your stack top still consists of B's. So there are still B's left in the stack that you are popping completely, not pushing anything else. So this expression tells us that your J's can be greater than K, because here you're creating this transition, right, which says B, the number of B's can be greater than number of C's, right? So this is, again, you can either go to the final state using this path or you can do it using this path. So when we went through this path, we got I less than J. When we're going through this path, what did we get? J greater than K. This is what we got, right? And it's a logical OR. Why is it a logical OR? Because from the starting state, you can either go to this path or you can go to this path. Either of these two paths are possible. So if you look at all the options, and no, there are only two ORs. Now look at the ORs here. I less than J, this condition is here. J greater than K. So C is the option. Simple. Right? So C is the right option here. Very simple. Okay, so this is a good question. Again, this is a slightly interesting question because we thought about, again, this is tricky also because if you're not careful with the transitions, you'll start making mistakes, right? I like this question personally. Okay, sounds good. So let's go to the sixth question now. Or non-CFLs. You have to be careful here. Which of the following questions are non-CFLs? Which of the following are not CFLs? Okay, that's important. Again, please be very careful with this. The question says non-CFLs. Again, please be careful with your options. I see a wide spectrum of these options here. I see A, B, C, D, all of them actually. So please be careful. I think most of the options are between A and D. Couple of B's and C's also, but mostly A and D is what people are thinking in between. Okay, so let me go into the solution anyway, just in the interest of time, because we have 4 more questions, some on undecidability, which are more tricky to explain, and for me also, because these explanations take time. Solving them is actually easy. Explanations are what takes time. So look at this. Very importantly, all of you who said A is the right answer, I think you're getting confused between OR and. If this was AND, then it's tricky. But here, look at this. You have A power N, B power M, C power K. So you can either, look at this, either this two have to be of different lengths or these two have to be of different lengths. So we have just seen this previous example, right? Look at this previous question. In this previous question, this is, again, in this question, it's about greater than or less than, right? But you have to compare A, B and number of B's and C's. And here we create an NPDA. So similarly, in this case also, you can create an NPDA if you think logically. What the NPDA does is, the NPDA non-deterministically either checks number of A's and B's, because it's a non-deterministic thing, right? Remember, we just said CFLs, we didn't say deterministic context-free languages. So you can actually generate an NPDA for this, which non-deterministically either chooses to check this or this. Very similar to what we've seen in the previous problem. So you can construct an NPDA which checks for this or this. Again, the OR logic comes because of the NPDA, very similar to the previous question. The architecture will look similar. Of course, the transitions will not look same, because here also we have this OR logic here. Look at this. So the reason we gave this question right after this is to confuse you slightly. And this is a CFL. This is a CFL for sure. You can construct an NPDA for it. Now look at this part here. This is slightly tricky, okay, if you're not careful with it. But I think all of you got this also right, which is W1, W2 lengths have to be same. So you push W1, after you process the rest of it, finally you'll pop W2 also, right? So that part, again, there is C here to help you with it. Okay, to help, there is the C which is not there in W1 and W2. So that can help you as a way to solve, to understand when you stop pushing your W1. Okay, so that part is clear. Then look at what you have here, this part. Look at this part here. If you notice this part, you have A power N, B power M, A power I, B power J, right? Look at this. And is there any relationship between, okay, there is this relationship. Look at this. N has to be less than equal to M. So you can check this. Again, keep pushing A's into the stack, popping when you have B's, then you can check if number of A's is less than equal to number of B's. Similarly, look at I and J here. What does I and J say? J has to be strictly equal to 2i. Even that you can check. And you can ensure that length of W1 equals to length of W2 by pushing this and popping this. So this also is a CFL. If you carefully think about it, it looks very big and daunting and complex at the outset. But if you break this problem into pieces, this is actually fairly simple. Again, there is also, you can actually draw a whole grammar for this. Okay, again, that's a good exercise problem. So for this, think about writing the grammar. I have written it when I was solving this problem just to be double sure, but think about it. You can actually draw a context-free grammar. You can actually write the CFG for it. So take it as a nice assignment that you can think of. It's not going to be trivial, but it's going to be fun to write it. Okay, so the third one here. Okay, so third one is simple, right? I mean, this is like straightforward, simple stuff. W1, W2, you have the separator also. The lengths have to be same. Keep pushing it. After you get C, keep popping it. It's very simple. You can also write the grammar for this. Let me write the grammar for this. So the PDA approach works, but let's also draw the grammar. So W1, W2 is AB, right? So you can do ASB. What all possibilities are possible? BSA, ASA, BSB, or C, right? Or C. The length can be 0 also, right? So C. That's it. I think this grammar, if I think about it. So whatever the length, right? So the length it generates here, the length it generates here has to be same. So we are saying just generate one character here, one character here. Yeah. So this sounds logical. Yeah. So this grammar can generate this language. Okay. Again, you don't have to write the grammar every time. Simple. Keep a stack and you can figure out that this is also context-free language. So none of this is the option. Right. So it's a simple question. If you're careful with it, it's actually an easy question, to be honest. So let's go to the 7th question now. Again, the question here is which of the following are context-free languages? That's important. Again, think about it from the stack perspective. Again, I see a lot of options here, so please cross-check your answers. I see B, C, D, A, all 4 of them. So please cross-check your answers. You can use pumping lemma for this, but pumping lemma proofs can be very lengthy. So think about it from the trying to create a stack and using that stack to solve these. I thought most people will get this question correct. Surprisingly, I see a lot of you are getting it incorrect. Again, please understand that which of the following languages are context-free languages? That's the question. Okay, I see some of you editing your answers also. Good, good, good. So let's go into the solution now. Okay, so let's see. So here if you notice, look at this, you have ij here, then you have ij. So if you think about from a stack perspective, right, you just push your a's, you push your b's. So your b's are on the top of the stack now. But you have to compare your number of c's with number of a's which are below b's in the stack. Look at it, imagine if you have 2 a's here and a b, right? The number of c's should be equal to the number of a's, but a's are below b's. Without popping b's, you can't compare the number of a's with number of c's, right? So that's one. Again, afterwards you have to compare b's with d's, right? So this certainly, if you think about writing a simple finite, again, this is a very simple strategy. Think about designing a finite automata plus stack to solve some of these problems. That's sometimes easy. So you can see that it's not possible, right? So certainly this is not a context-free language. Okay. Second, let's look at this now. So the moment 1 goes, let's start eliminating. So this is not an option, this is not an option, right? So 1 is not a context-free language, right? So either you can pick 2 or 3. Okay. Now it's very clear. Again, you can look at this also. You can compare number of A's and B's, right? Look at this. You can compare number of A's and B's. But after you finish this comparison, now you have to compare number of B's with A's or number of A's with A's. But let's assume you pushed A's now. For every 2 B's, you pop an A. Then by the end of it, you don't have any more A's to compare the number of A's here, right? So even if you think about it from the from the stack perspective, even this is not a context-free language. So this option also goes. So you're left with none of these. But let's also understand this part now. So this part, WW reverse, we know we can construct a non-deterministic PDF for this. That part is simple. But the other W which is still there, look at this. Here what happens here, WW reverse, you'll keep pushing W's non-deterministically because you don't know where, because there is no C in between, right? Non-deterministically, at every stage, you'll think that it's the middle of these two. You can do this using a non-deterministic PDF. It's a standard example. But then the third W is what messes things up, right? So this is also not a context-free language, right? Since none of them are context-free languages, the option is D. I thought this was, I don't know. At least when I was solving these problems myself, I thought this was one of the easier ones. But yeah, there could be different. Again, always think, grammars is one way to think, but grammars also can take time. So if you can think about it from the perspective of finite automata plus stack, try to design a finite automata plus stack based system to accept these languages. In all three of them, you can't construct them, right? So sounds good. So let's go to the 8th question. Okay, I hope this is clear. Okay, so yeah, everything is in the screen. This is a slightly lengthy question. Again, this was one of the harder questions actually. This took me some time. Okay, the 8th question took me almost 3-4 minutes for me to solve. So again, probably I am not practiced enough nowadays. That's why it might have taken me more time, but let's see. Again, if you think one of our answers or options is incorrect, please do email us and we'll look into them, because it's hard for us to do it in live because there are also other questions that we have to solve. If there is anything where you find a mistake, please do email us at gatecsc@appliedcourse.com. We'll surely look into them. Again, there might be one odd case where we'll make mistakes and we'll correct them. Okay, I see a few of you have put in the answer for the 8th question. Some of you are still discussing about the 7th question. I understand that. Again, if we have made a mistake, we'll call it out in the comment section. We'll pin that comment and clarify. We have done this in another previous session. I think C programming. The answer is correct, but my explanation was erroneous because I misread it while I was explaining it. So if there is an error anywhere, we will clearly call it out in the comment section. Okay, most of you are saying B is the answer. But some of you have also said A and D also. So let's take a few more seconds and then I'll go into the solution. Thankfully, the options are easy to eliminate. But this question can be made quite hard if we jumble up the, if we make the options harder. I think the options are easy to help you. Okay, so let's get into the solution now. I'm also looking at the comments. If there is a good comment or a response from somebody, I'm also, again, I don't want to, for tricky options, it's hard to explain it in live without preparing through it. So if somebody gives a good explanation, I'm trying to double down on it. Anyway, sounds good. So let's go into the solution here. Again, good to see some of you responding to other students' question, not just our team. And that's helpful. I mean, that's a constructive part of these public sessions. Okay, so let's look at it. So what do we have here? We have S generates A, B, S, D or T. It can also generate T's. Okay, now, okay, so all these are greater than equal to 0. So I don't have to worry too much about this. So I have to just worry about number of A's, B's, C's and D's. Okay, there is also this part here. We'll see. All these three look very similar or somewhat similar. This looks slightly hatke or slightly different for those of you who don't understand a little bit of Hindi that I know. So let's think about this, right? So what is this doing? So now B can generate. So look at this. If you have A, so look at what T's can, what S can generate. S can generate T's also going forward, right? Look at what B's can generate. Okay, so you have A and D. The starting has to be A, the ending has to be D. Okay, that part is clear. So this option you can eliminate, right? Can you eliminate that easily? No, because it can also generate T. You can't simply eliminate it, okay? Because it can also generate these. Okay, you have to be more careful here. So let's go into this. So you have, okay, let's go into this. S generates this. So you have A, you have D here, you have BS. Now what can B generate? S can, so let's see what S can keep generating these, right? So S can again generate A, B, S, D, or it can generate T, right? So let's assume S generates these. So what do you have? Your BS, now look at this, B followed by A can be replaced with AB. So you're now swapping it. So what can you get here? You can get AA, right? I mean, if you think logically, this A followed by B, B followed by A can be made AB. So you get AA, BB, SD. That is possible now, right? So because look at this, BA, I just replaced it as AB. Now we have this, right? So let's look at more things now. So number of A's, number of D's is here, right? You have SD. Now what can S generate? B, S, B, A. Okay, so let's go through this. Okay, so you have A, B, S, D. S can generate T also, right? So let's also remember that fact, okay? That S can also generate T. What can T generate? Look at this. What can T generate? T can generate BTC. It can keep generating B power M. Look at this. It can keep generating B power M, C power M, right? It can keep generating these. At the end of the day, T can be replaced by epsilon, right? So it is generating B power M, C power M here, but you have your D's here now, right? So you have your D's here. S can generate this, right? So one way that I thought about this problem, again, the way I solved it was by eliminating options, okay? But let's also try to solve it using first principles, right? Let's see, A, B, S, D. S can generate T. T can generate B power M, C power M, right? So C power, but you have also D here. Okay. So now what happens to B? What can B generate? Look at this. B onto itself can't generate much, but B, when you have A, you can swap this order. BA can be written as AB, and BB can be replaced with terminals here. Similarly, if you have BD, you can replace it with BD here. Okay, so this part teaches you that what you will end up with is, you will end up with, because A's can be generated as much as you want. So you will end up with a scenario where you get A power N, okay, because this B is AB, remember, BA can generate AB, right? Again, this B now, if it has another B on the side, that can become BB, right? So that can become BB now, okay? So that part is there. The other thing that you have to be careful about is, so at least from the high level overview of this grammar, it looks like this. The number of A's and number of D's, look at this, if you look at it, the number of A's and number of D's will be the same, but that's not helpful because you have A power N, D power N, A power N, D power N here, A power N, D power N. That's not helpful in eliminating options. So another way to think about it is this. Let's construct an example. While we're constructing the example, we'll keep trying to eliminate the options. That's another way. Okay, so A can generate A, B, S, D. Okay, so this can now go ahead and generate, let's say this can generate this S. Let's again use the same thing. You can generate A, B. This S can generate A, B, S, D, A, B, S, D, D. Okay, so now you can swap this BA, you can swap this and you can get AA, BB, S, DD. So you're getting this pattern now, that number of A's. Again, I'm trying to construct examples so that I can eliminate some of these options. Now, if you notice this, by just looking at this string, let's assume B, so you have BBS, right? So if you think about it, if S is replaced by T, so, okay, so you get BB here. Now, after BB, what can we do here? Let's assume this S now is, again, I'm just thinking aloud while I'm solving it. AA, BB, S, DD. Now, what happens here? You have BB here. So, this will now generate, so let's assume this S, let's represent it with T. Okay. Again, I'm just thinking aloud while I'm solving it. So, I've replaced it with T. Then T itself can replace BTC now, right? So let's do AA, BB, BTC, DD. Okay. Again, I'm trying to see which options. Again, from a pure gut feel perspective, we know that A's and D's have to be same. Okay, because of this, because A's and D's are here. From a pure question perspective, this seems that this has to be true. But with that, I can't eliminate options. Okay, so let's continue the construction here, right? So you have AA, BB, B, T, C, D, D. Okay, it looks like, if you notice this, look at this, BB can generate B's now. BB can generate B's now, right? Similarly, T can generate epsilon. Let's assume I replace T with epsilon. Let's just see that, okay? So you get AA, BB, B, C, DD. Okay, you get this. Okay, sorry, where is my, okay, you get D here. Again, I'm trying to construct an example keeping these four things in mind. Now, once we get this, I've just replaced t with epsilon because we have that option now. Now let's look at this. You have A, you have double B followed by B. So what we can do, BB we can replace with, okay, so from here, so this is AA, BB, BC, DD. So from here we can do one more thing. We can do AA, B, B, right? So BB, again B, C, D, D. Because this BB can be replaced with double B. Now you have AB. AB I can swap now. Okay, AB I can do BA. Right, so I can do BA here. So this will generate AA, this BB I can do it as, sorry, B followed by B, I can do it as single. Okay, so let's do this. AA, BBB, CDD. Okay, I can do this, right? AA, BBB, CDD. Yeah. Yeah, this BB can be replaced with BB now. So if you notice here, what is this? This is A square, B cube, C power 1, D square. Again, I followed these specific rules primarily because the reason I followed this is, look at the options we have. This says number of B's and C's have to be same. But I try to, when I'm constructing this example, I try to ensure that, try to avoid that case where number of B's and C's are the same. So if you notice this, number of B's and C's are not the same here. So this option can be ruled out. Again, this is a slightly lengthy process of constructing using counter example. Okay, so if you notice this option now, what does this say? Number of A's and number of B's have to be double. But in our string that we constructed, they are not double. So this option can also be ruled out. Right? If you notice this option now, this says B power M, C power M. Okay, or because it's union, A power N, D power N. This language will never contain this string. So this also can be ruled out. This word here that we have perfectly fits into this because N is 2. N plus M is 3, M is 1, D is 2. So one way you can think about, again, there are multiple ways of solving this problem. One way to think about it is construct an example, and while you're constructing this example, you try to rule out a bunch of options. Again, this example, as I mentioned earlier, is slightly harder, primarily because you have these expressions like these. These expressions like this are what makes grammars hard. Okay, because coming up with counter examples and thinking intuitively from a grammar perspective becomes much more harder then, right? But in this case, while again, this is a case where you have to construct a counter example carefully. Again, while I'm constructing this example, one thing that I thought of is, do number of B's and C's have to be same or not? Because if they have to be same, I can eliminate B, C, D, all options, or at least I can eliminate B and C, right? So you have to be careful when you're thinking of those options. The example that you create, try to rule out options, try to create an example such that you can eliminate options here. Again, this grammar is specifically tricky because of these three rules of the grammar, right? Sounds good, okay. Okay, so let's go to the next question. Okay, now we are into undecidability territory. Okay. Again, some of you are still stuck in question 7. Leave it right now. This video will be available on YouTube. You can rewatch it, rethink about that question later. Please, let's solve the 9th question which is ahead of you. Please stop worrying about previous questions. If there is an error, please email us. Also, some students have corrected some of the arguments that other students have made. Our team has made some corrections here. So please don't get stuck with the previous question. Let's move on. You can think about that question after the session is over. Okay? This is a simple question actually about undecidability. This is a simple question about undecidability, guys. Okay, many of you got it. Sorry, my bad. I just scrolled it by mistake. Sorry. Okay. Okay, I think most of you got it correct, and let's go to this, right? So this is a very simple, again, we have for decidability problems, right? So there are two approaches of solving it in GATE, especially most of GATE questions. One is, you know, this whole big table that we have discussed in our course videos. Again, I'll show you that table in a minute or so, where we discuss various properties. This is the table. So we say for regular languages, DCFL, CFLs, context sensitive languages, recursively enumerable languages, a bunch of properties. Which of them are decidable, which of them are undecidable. And we explain the intuition and proof of some of them, if not all of them. Okay, there is also a previous video where we explain what is membership, what is emptiness, etc. So this sort of table is very, very useful. Okay, look at this. For regular languages, membership is deterministic. Right? So you can sorry, not deterministic, decidable. I'm sorry. I'm getting the deterministic PDA thing in my head. So it is decidable, right? So if you notice for this, what can we do? It's very simple. Imagine, because membership in regular languages, see, so we can construct a Turing machine M, to which if you give W, if W belongs to L, look at this, because D is a deterministic finite automata, right? If W belongs to L, it will accept, or else it will reject. So it will accept when W belongs to language generated by D, right? Otherwise it will reject. W doesn't belong to this, right? Because membership in a regular language, which is what DFS generate, is decidable. Now here it says the opposite of it. So what can we do? It's very simple. Whenever you have accept here, you reject. You just swap the result here. So whenever W belongs to LD, you reject. Otherwise, you accept. When you do this, what happens? You are accepting when W does not belong to LD. You are rejecting when W belongs to LD. And that's what you want. Look at it. Your deterministic finite automata, and you're given a word. D is a DFA and W does not belong to LD. So because we know that regular languages, right, membership, this is nothing but a membership problem in regular languages, right? Membership problem in regular languages is decidable. We know that. Which means there exists a Turing machine that can do this. You just make accept, reject, reject, accept, then you're done, right? So to solve decidability problems about languages in an examination setting, because proving this could become very lengthy, what we recommend our students is, remember this table. Again, don't just remember it by heart. It's very easy to remember this table if you understand some concepts that we have discussed in detail. Some of these things we prove in the course videos also. So if you remember this table, then this whole question is about just applying it and constructing a small thing on top of it. Look at this. What did we do? We use this logic. We use the property that membership in regular languages is decidable, right? Now we just swapped accept to reject, reject to accept, and we're done, right? So whenever you have undecidability problems about languages, two strategies. One is use the big table about which property is decidable, which property is undecidable, and always think about it from constructing a Turing machine. Simple Turing machines, nothing very fancy. Okay, again, construct, what is a Turing machine? It's a computer program at the end of the day. Whatever computer programs can do, Turing machines can do, right? From the perspective of decidability, right? So again, a lot of people mess up decidability questions, but if you just follow these two steps, they're extremely easy to solve. Now let's look at this option. So this is decidable, so we know that. Okay, so this option can't be right. Let's start eliminating options also. So you have D comma Q, where D and Q are DFAs, and the intersection is a null set. Now we know that if you have two DFAs, which are accepting languages LD and LQ, we can always construct an other deterministic finite automata. Let's call that finite automata P, which accepts the intersection of these two. Look at this. If you have two deterministic finite automata, again, this is something that we discuss in deterministic finite automatas in our course videos, right? if you have two deterministic finite automators, you can always construct another DFA called P, which accepts languages that, which accepts the intersection language of these two machines, right? You can easily generate that. Okay, it's a very simple process to generate it. Now what does it say? It says the DFA P, again, remember, we can construct this DFA P such that the language accepted by P is same as language accepted by D intersection language accepted by Q. Now, there exists a P. Now, what is our question now? Our question is now modified as, again, you can write a computer program to do that, which means there exists a Turing machine to do this. There exists a computer program or a Turing machine that can construct this P. Now, given P, so we have a machine M that constructs the P. So, it takes D and Q as input, it constructs P. Now, once it constructs P, whether the language accepted by a machine, again, remember P is DFA, which means it accepts regular languages. Whether a regular language is empty set or not, again, this is decidable. You can construct another machine D, M dash, because that's basically the emptiness property, right? Look at this. We talk about emptiness property of regular languages is deterministic. Or sorry, is decidable. I keep using the word deterministic. Is decidable, right? Emptiness is decidable. So now what do we have here? It's very simple. If you think logically, you have one machine that will generate P, another machine which will because whether a regular language is empty or not can be decided, right? So it is possible to construct a sequence of two machines to do this. Again, whatever, this is like calling one function followed by another function in a computer program, right? That's cool. Let's look at the third part here. This says equivalence of two Turing machines. Now again, so this is decidable, this is decidable. What about 3? Now again, this is a property that we discuss in the course videos extensively. Look at this. So equivalence, the equivalence property for Turing machines, which basically means recursively enumerable languages, all these properties are undecidable, including equivalence, right? Because I mean, again, we discussed this in the course videos about the proof. I'm not going into the proof here because that could be lengthy, but it's very simple to, it's a very simple property of Turing machines. So given that, you know that this is undecidable, this is decidable, this is decidable. Yes, finally, I'm not saying deterministic, I'm saying decidable. Okay, so what is the right option here? Option B, right? So that's the key here. Okay, let's take this final question now. Oh, this is also a good question. This is a slightly lengthy question, so take your time, it's okay. But it's not hard. If you know the foundations of Turing machines and decidability, this is straightforward. Only 8th question I think I felt was slightly lengthy. Again, I see all options here, A, B, C, D, okay. So please think about it. Many of you are saying C. What is C? 2 and 3. Come on, that's straightforward, guys. 2 is surely not right. Oh, you can eliminate all the options by just looking at second option actually. Two is given intentionally because it's something that many people think is actually true, which it is not. Anyway, so let's go into the solution, right? So, okay. So let's look at it. Every recognizable language can be recognized by a Turing machine that either accepts or loops but never rejects. And this should be simple to construct, right? So let me construct it first. So let's assume I have a recognizable language L, right? So I have a Turing machine, right? So I give some word, right? So what does this do? If W belongs to L, so this M is a Turing machine, okay? So this M is a Turing machine. So because we know that L is a recognizable language, if W belongs to L, it accepts, right? If W does not belong to L, it can do two things. It can either reject or it can go into an infinite loop. That's the definition of a recognizable language, right? That whenever there is a word that belongs to it, we'll always accept. If the word doesn't belong to it, we'll either reject or go into infinite loop. This is the definition of your recognizable language. Now, what are they asking us? Every recognizable language can be recognized by a Turing machine that either accepts or loops but never rejects. And that should be simple, right? Look at it. So what do we want? Now we want to construct another Turing machine which accepts or loops but never rejects. And that's simple. So what do I do now? Look at this. I just create this into I just create another Turing machine. Turing machine, you can think of it like a computer program. Okay, this computer program contains this computer program. So whenever it returns accept, we will accept. Whenever it goes into infinite loop, we will go into infinite loop. Whenever it rejects, I'll just add an infinite loop after that in the code. Because what do we want? We want every recognizable language can be recognized by a Turing machine that either accepts. So whenever it accepts, we'll accept. We will never reject. So whenever this Turing machine, whenever this machine M rejects, I'll just add a while infinite loop there and get stuck there. Right? So now what do we have? We have a machine that always accepts if W belongs to L. If it doesn't accept, it always goes to the infinite loop without rejecting. So we have constructed a new Turing machine M dash for this. Right? So this is obviously true. So 1 is true. What about 2? Again, this is actually fairly simple if you think about it from an example standpoint. Think about sigma star. Sigma star is a regular language, right? Sigma star is all the strings in the language. Sigma star is a regular language, right? Because you can actually write the regular expression for it. Now sigma star on some alphabet, it could be binary alphabet, whatever alphabet you are using, given sigma star, right? Take a language L that represents a Turing machine. This language is a strict subset of sigma star. Let's assume I have a language L, right? That represents a Turing machine, some Turing machine of your choice. Now, or in other words, let's look at it like this. I have a language L that represents all Turing machines. This is obviously a strict subset of sigma star. Sigma star is regular. So remember, sigma star, look at this. If a language is decidable, which means in other words, because this is a regular language, I have a I can write a deterministic finite automata. Right? So this is decidable. This language, membership in this language is decidable obviously. But there is a strict subset of it. This is a subset of it. This language which contains expressions that represent valid Turing machines, this language, something belonging to this is surely not decidable. So this surely is not true. So the moment you eliminate option 2, this goes, you are left with only option A. Right? So let's look at option 3 also. Now, I hope all of you understand what this symbol means. It means you can write a mapping or a function, right, to reduce it from this to this, right? For example, again, this is a slightly tricky case, so I just wanted to explain it. So what does it say? It says, look at this, let's write it. Let's assume W belongs to A, okay. What does this mean? This means mapping reducibility. So what does mapping reducibility means? I have a word that belongs to A. Then I can create a mapping function f such that f of W belongs to B. That's what it means, right? Again, this f itself is a computational function. Okay, it's a computable function, to be more precise. This f itself, you can represent it using a Turing machine. It's a computable function. Okay, so now what do you have? Okay, so it's a computable function. That's why it's called mapping reducibility, right? So now what do you have? Okay, what does it say? If A mapping reducible to B and B is a regular language. So let's try to think about a counter example. What is B? What can be a regular language? Let's take a very simple regular language, right? So let's take a regular language like, okay, 0 star 1 star. Okay, I have a regular expression, hence it's a regular language. Now let's take A here. Okay, so let's assume A is 0 power n 1 power n, such that n is greater than or equal to 0. This we know is surely not regular, right? We know this, right? This is like a CFL, a context-free language. Now what does it say? If, look at this, there exists a function. So if there exists a function that can map every word in A to a word in B, and it says if B is regular, then A is also a regular language. So I'm trying to prove this incorrect by taking a counter example. Okay, so here you have B, which is regular. This is not a regular language. So I'm trying to prove it by contradiction. Now, how can I construct my mapping function now? So imagine if I'm given W that belongs to A, what does my mapping function do? My mapping function, right? My mapping function can simply return 0, 1. Okay. If W belongs to A. So let's assume, okay, so let's look at this. Okay. So let's assume I'm given W. So there are two possibilities. W belongs to A. If I give to this mapping function, which is represented using a Turing machine, I can just output, if it accepts, I can just output 0, 1, because I know 0, 1 belongs to B, right? I just output this. If W does not belong to A, then my mapping function rejects it, and rejecting basically means it will output 1, 0, and I know 1, 0 does not belong to B. Right? So I can actually construct this mapping reducibility as follows. It's a very simple construction, right? So now if you take this simple construction, now what do we have? I have constructed a counter example to this statement. How did we construct it? We have B as a regular language. A is not a regular language, but we have a mapping reducibility from A to B through this construction. Look at this. This is a construction of mapping reducibility from A to B, right? B is regular, but A is not regular. So we constructed a counter example here, right? Hence this statement is also incorrect. In an examination setting, typically what happens is, for this problem, if I were to solve this problem myself in an examination setting, I quickly recognize that A is the right option, 1 is the right option, 2 is the wrong option. The moment, that's why whenever I strike off anything, I try to strike off these options also. 3 is the tricky part. Again, some people may not even know mapping reducibility, or may not be able to think about this construction. So this question is given in such a way that if you can eliminate option 2, you are left with only option A. So in decidability problems, whenever again, most decidability problems come in like this, try to eliminate options, because sometimes you don't have to solve each of the options, because sometimes like solving this option itself is like could take a lot of time in the real world, right? While I have explained it to you here, it could take a lot of time, right? So try to always eliminate options. Again, very importantly, if there is any error in this, couple of important things as we are closing out. So if there is any error in the questions, some of these have already been answered here. So if there is any error in any of our solutions or anything, do email us at gatescsc@appliedcourse.com. You can find our email address on our website also, gatescsc@appliedcourse.com. Please email us, and if there is any correction, we'll put a correction under this video. Number 1, any general questions, whether it is about our test series, about our course, please reach out to us and we'll try and do our best to help you with it. And again, you can call us on this number or email us. To be very clear, whenever we get emails, we try to give first preference to students who are already course registered, because we promised them that their questions will be answered first. right? As we are coming closer to exams, we may not be able to answer every question from every student, but we'll try our best. Okay. Sounds good, folks. Thank you very much. Thank you, and see you next week. Again, next week will be compiler design, as I've just mentioned.